What's up, everyone? It's Calc Time with Miss Wesley. I hope you're having a great day. Today, the first thing I want to do is get a chance to practice with these volume of solids of revolution problems, specifically the ones that we would have started the other day, where you're revolving a region around a line, like I see on page 8 here in your volume packet, a line that's not the x or the y-axis, some other line, like y equals -6 or x equals 4 as your axis of revolution. So while you're opening your volume packet up to page 8, maybe getting yourself situated, I heard a quick joke that I had to share. I saw a fish the other day with a bow tie, and you know what? That's what I call sophisticated. Let's take a look at number 4. So first thing we do in all these questions, just to get our head around what the shaded region even looks like, is to sketch a little graph. We've got y equals 3 minus x squared. And for that, I'm envisioning an upside down parabola that's shifted up 3 units. So maybe step 1 could be, just to get this shaded region down, let me shift this parabola up 3 units, and I'll draw it opening down from there. So this is y equals 3 minus x squared. Now we want to bound this region with this curve that we just drew and the line y equals -6. So I can come down further, 1, 2, 3, 4, 5, 6 units, and then close it off with this line, y equals -6. So this just gives me a better sense for starters of what region we're revolving at all. I'm going to shade this in blue, this entire region between that curve and the line y equals -6. And this is your line of revolution, right, in 2D. Okay, so we could kind of start setting up the integral, but in a second, I want to make an attempt to draw what this would look like in 3D if we did revolve this region. So let's think. For days now, we've been working on volume of solids. We're using this disk method so that when all said and done, we're going to be integrating, right, area of a circle for the disk method. So a pi r squared, let me just leave room for the r part. And this one has a horizontal line of revolution. Y equals -6 is a horizontal line. So we'll do everything in terms of x's. We need x values for these limits of integration, and we need x expressions for what that radius is going to be of each disk. So we got to think, let's get those limits of integration. We want to know the x values where these graphs are going to coincide. We need these intersection points. So you can use a calculator to get them, or we can just set the two expressions for y equal to one another, right? For intersection points, like we've done in other problems, intersection points, we can set this expression for y, so 3 minus x squared, equal to this expression for y, so equal to -6, and solve that out. So -x squared, I guess, equals -9, and you get x squared is just 9. So I like intersection points at plus or minus 3, right? At 3 and -3, and we can put those right into our integral for volume. X values are going to go from -3 to 3. Okay, so now the big question is going to be, we integrate pi r squared. So now we're going to work on the picture and decide what would be a good expression to write for the radius of the disks that we're going to see in this 3D figure. So imagine this shape getting revolved around the line y equals -6. You'll have this symmetric portion that comes below the x-axis. Didn't draw that perfectly. You have these disks that are stacked up small to the two sides. It's going to be big in the middle, right? Small to the two sides. In maybe yellow will show up okay, because I've already cluttered up this picture a lot. You've got these yellow radii that are going to be the distance up to the top of that red curve. And the big difference in problems like these that we've kind of just started working on are that when you have some line of revolution that's not a coordinate axis, you generally have a top function, a function that bounds the shaded region from the top, and you have a bottom function, a function that bounds the shaded region from the bottom. So for this one, reminds me of those area questions where we're going to integrate top minus bottom. For this yellow radius, right, which kind of changes shape throughout, we can use top function, 3 minus x squared, subtract the bottom function, so minus -6. That would be a good expression for just this distance that's going to represent the radius. And we can simplify this a little bit. This is like saying 3 minus x squared, and then we could say plus 6 because it's minus a negative. So the rest of the problem, now that we've done the hard work for the setup, is going to be all about simplifying and integrating. Feel free to pause the video and take your time and then check back in to see if we're getting similar expressions. So I like to move the pi outside of the integral sign as a constant. And we're writing -x squared plus 9, which is being squared in that integral. And then probably better to get rid of the parentheses too. So you've got still integral from -3 to 3. We want to square this out with itself. So we can square the first term and get x to the 4th. We can take double the product of the two terms. So minus, I think, 18 x squared, and then plus 81. There is no reason that you have to go that quickly through that algebra to get that squared out. You can take your time, pause, and just make sure that that looks good for what that would be squared. And then I think what's left is to integrate. So we'll do it with all three terms. Take it up. X to the 5th over 5 minus, this is going to be x to the 3rd, and then 18 over 3. We could call that 6. And plus, let's just make this 81x evaluated from -3 to 3. And I might have to scoot things up to have enough space for this. So you know you plug in the top number, we're going to subtract what we get when we plug in the bottom number. So this is pi, and then times 3 to the 5th over 5 minus 6 times 3 to the 3rd, and then plus 81 times 3. And we are subtracting, I'm going to go minus in an extra set of parentheses, -3 to the 5th over 5 minus 6 times -3 to the 3rd, and then plus 81 times -3. Okay, pause here. This is a perfect spot to pause and just carefully type this into the calculator. Hit math frac. I would do that too. And you end up hitting math frac and just getting a big fraction, 1296 over 5. And again, a decimal would be fine for this too. So this is the amount of cubic units that would be in this volume, 1296 pi divided by 5. Okay. I want to look at one more on this page where the line of revolution, it's not a coordinate axis, and this time it's a vertical line. So it's a vertical, we'll say for number 5, line of revolution. And all that tells me is, yikes, I got to do everything in this problem in terms of y's instead of x's. So I'll just integrate, we'll say in terms of y. So our limits of integration will be y values, and also our expression for what we're going to integrate is going to be in terms of y. So I like to, for these sideways regions especially, I like to go to Desmos just to double check my shaded region, how it's going to look. So it's x equals 2y squared plus 2 is your sideways parabola, and we want to bound that off. We want to shade the region between that and x equals 4. This is what I want to sketch, and I want to shade that little tiny bit of the region enclosed by those two curves. So it looks like, and especially good to know these y values at these intersection points, that this graph is going to go from the point 4, 1 all the way down to 4, -1. Okay, so I'll go back and transfer this to our graph. This thing is shifted over a bit, right? And it opens to the right. Here's x equals 4, and you've got this expression that we just graphed. So we graphed x equals 2y squared plus 2. And really important to note those intersection points here and here. We're going from y equals -1, we said, up to y equals 1. So that'll go straight into our integral. When we integrate to get volume, I know I'm going between these two y values, -1 to 1. And this is our shaded region, like that. And here's where we want to put it into 3 dimensions. We want to spin this around this vertical line, around the line x equals 4. So we're spinning it around that region. You're going to get sort of that Christmas tree ornament shape. It'll come around to the other side, a large disc in the middle with a large radius, and then smaller radii as you go up and as you go down the shape. And we'll get the radii in a second. So similar to the last one, you're still integrating pi r squared, but this one we're doing in terms of, we said all y values instead of x values and all y expressions. So I'm going to integrate with respect to y this time instead of x. Now I remember in the last question, we focused on a top function minus a bottom. This seems like it's sideways, so I think I want to think more about a right function minus a left function. If we talk about these radii, they're just the little horizontal distance that I'm highlighting in yellow here from this right function, x equals 4, that's a little hard to see, to this left function, I'll call it, 2y squared plus 2. So let's try that. I want to put this right next to it as my radius. We'll say radius this time sideways equals right function minus left function. So 4 is the function bounding the region from the right. And then this expression is the function bounding the region from the left. I guess I shouldn't say function, but I can say relation bounding the region from the left. So we have a little bit of simplifying we can do too. We can call this negative 2y squared. And we can say, what do we have? Plus 4 minus 2. So we'll say plus 2 as the second part to that. And from here on out, we've got a little bit of algebra to do, a little bit of simplifying with the squaring, and then we want to integrate to find this volume. So it was convenient last time to push the pi outside of the integral sign, and then we want to slowly and carefully FOIL through so we see what terms we have in this trinomial. So this will be square the first term, so square negative 2y squared, so we'll make it 4y to the fourth. We want to do double the product of the two, so minus, this would have been 4y squared if we multiplied these, so we'll make it minus 8y squared. And the last term should be just 2 squared, should just be 4 that we want to integrate. So again, that was a little bit too quick. Take that slowly so you can be really careful with those terms, and let's integrate. We can drop the integral sign. We'll go up a power, 4/5 y to the fifth. How about this one going up a power, 8/3 y to the third, and then plus 4y. And this gets evaluated from y equals -1 to y equals 1. So the 1 gets plugged in first. We'll show the plug-in, pi times 4/5 times 1 to the fifth, minus 8/3 times 1 to the third, and then plus 4 times 1. And then the same thing, but plugging in a -1. So 4/5 of -1 to the fifth, that's negative to an odd power, will make it a negative. This will change it. 8/3 times -1 will give us plus 8/3. And then 4 times -1 gives us a minus 4. All this gets carefully typed into the calculator. You can get the lowest term fraction and then just include pi in your answer. So you get a 64/15, and that gets multiplied by pi. 64/15 cubic units of volume enclosed between the shaded region when it's spun around that axis of revolution.